Newton's second law. While Newton's first law describes objects that are moving with a constant velocity, which might be moving or it might be at rest, Newton's second law describes objects for which an unbalanced or a net force is acting on them, and therefore they will not stay at a constant velocity, but they will accelerate, and they will change either their speed or their direction, or possibly sometimes their shape. So a statement of Newton's second law is here and states as follows: where there is an unbalanced or resultant force on the object that is free to move, the object will accelerate, it will change its velocity. The acceleration is proportional to the resultant force and in the same direction. So let's unpack that a little bit. Here we have an object, just a little ball, and it has an unbalanced force on it. Let's draw a force arrow here, F. That is not balanced by a force in the other direction. And Newton's second law says that if that force is acting on the object, then it will cause an acceleration which is in the same direction as the unbalanced or resultant force. So if the force is vertically downwards, then the acceleration will also be vertically downwards, and the object will accelerate in that direction. It also says that the force is proportional to the acceleration. That little symbol in the middle there that looks like an alpha means proportional, which means if you double the force, this will lead to a doubling of the acceleration. That's what it means that the two quantities are proportional. They go up in the same proportion. The other thing that affects the rate of acceleration is the inertia of the object, as we talked about in the video on Newton's first law. So with an object of higher mass, higher inertial mass, so if this object has more inertia, i.e. more mass, and the force is the same, then the acceleration will be less. So there's a relationship between the mass and the inertia, or the inertial mass and the acceleration, that links all these quantities together, all three of these quantities. And mathematically, when we put all that together, we end up with this equation here, which is an expression of Newton's second law. And it says that the resultant force on the object, F, will be equal to its mass, and this is the inertial mass, effectively how much inertia it's got, multiplied by the rate of acceleration. And so hopefully you can see from that equation that if you have a specific resultant force F and you have a larger inertial mass, you'll have a lower acceleration, and vice versa. The two relate to each other in that way. Okay, now the other important thing to point out here is that this is the resultant force on the object, the unbalanced net force. So an object might have two forces on it. It might have a force going in this direction, which might be, 20 newtons, and it might have a force in this direction, which might be 10 newtons. And obviously the resultant force then will be 20 minus 10, which is going to be equal to 10 newtons. Technically, of course, if we look at the vector nature, this will be minus 10 and this will be plus 20 because they're in opposite directions, so we can denote that by the signs. And what we would then do would be to add them up as vectors, which effectively has the same result of being 20 plus minus 10, which is 20 minus 10. So in all effects, we have a resultant or a net force of 10 newtons, and that's the one that is important and the one that goes into Newton's second law. So the resultant force on the object is equal to its inertial mass, or just its mass, multiplied by the rate of acceleration. In symbols, it's usually written like this, where we have net force, or F net, is equal to ma, or just F equals ma, we usually call it, but it's important not to forget that this is actually the net force there. So let's just do one quick example of using that equation. So it says here, calculate the acceleration. So A is what we want. Calculate the acceleration of a 750 kilogram motorbike. So that's M. If a driving force of 2,000 newtons is applied to it in the forward direction and a 500 newton frictional force acts in the reverse direction, what direction will the acceleration be in. So let's calculate the acceleration first. So let's draw a free body diagram for the motorbike. So just draw a little circle with the two forces on it. So we've got well, let's assume it's going to the right. So we've got a 2,000 Newton force in the forward direction, and then we have a 500 Newton force in the reverse direction. So we can say that the net force is equal to, well, let's do it with the vector signs added in. So we have 2,000 plus 2,000 acting to the right, and minus 500 because it's acting to the left. So the net force would be the sum of those, which is going to be 2,000 plus minus 500. So effectively 2,000 minus 500, which is going to be 1,500 newtons. Okay, so we can then put that into our equation for Newton's second law and work out the acceleration. So I'm going to rearrange it down here. So we've got acceleration is equal to net force divided by the mass of the motorbike, which is going to be our net force of 1,500 divided by the mass of the motorbike, which is 750 kilograms, which is going to give us an acceleration of 2 meters per second squared. Okay, so that's how we use Newton's second law to calculate accelerations and so on.